is stock span problem that uses the concept of array and stacks. So what we have given an array and where each element represent the stock price of a given particular day, and we need to calculate the stock span for each day. So the span of stock on a particular day is the number of consecutive days before it, like including the day itself, and whether the price was less than or equal to the price of the stock today. So what we will do, it's sort of a like problem that is a little bit variated for that we've earlier done the next greater element sort of pattern. We will use the monotonic decreasing stack in that case and try to solve this in a linear time. So if you see, we have given a price of the stock for each day, and what we're doing, returning the size and the price list to the uh, function calculate span. And if you see, we are just creating an empty stack. And so the approach of this problem, what we will do is create an empty stack and store the indices in that, so that and we have to traverse an array from left to right, and pop while stack top price is greater than the current price. If that's the case, we will just pop it out. Or if it is empty, if it is not empty and it is greater than the, then we will pop it out. If it is empty, then we have nothing to pop out. And so what will happen is that the span is equal to the current index minus top stack top index. So to get the span, um, to get the span, the stock span, we will have to like um, minus the current, like minus the stack of like top index from the stack from the current index, and we have to push the current index into the stack then. So let's also dry run this thing. Suppose if we have prices of the stack as listed in the list. So on the day 0 we have the 100, so stack is 0 and span is 1. Again, the price is becomes 80. The stack contains 0 and 1. The one counter like how we count, we print one from here, like one from here, and then what it does, the stack becomes 0 and 1, then span remains 1, then it's come 60, 0, 1 and 2, stack remains 1, and after that it's 70. Then if we see its order, that it keeps on decreasing, but when it comes 70, it changes the order. So it becomes 0 1, and it will remove, pop the pop the stack, pop the second 2 from the stack. So our stack becomes 0 and 1, and our span becomes 2. Then it again comes 60. So we have 0 1 3 and 4, and our span becomes 1 again. Then it comes 75, again 0 and 1, and our span becomes 4. And then it comes 85, and then our stack becomes 0 and span becomes 6 by the formula that we are using, the current index minus the stack top index. So what it does, if you see the current index 3, it will minus with the span index, that becomes 1. And then when it again it does the same uh, with the other like fourth iteration, the current index minus the stack top index, it will print the other number like 4. Suppose if we have like if we minus 1 from 5, it will print 4. If we minus 0 from 6, it will print 6. So the space and time complexity of the this algorithm is O of n. And let's also run this code and check if what it's gonna print. So here we can clearly see that the 1 1 1 2 1 4 and 6. So at 2 we are getting at the 70th position, 70th, like at the third iteration, and we are 4 getting at the fifth iteration, and 6 at the sixth iteration. So it when it deducting it from the like particular you can say current index while calculating this span, the ith current index, and from the stack top. So when it deducting that, it just printing the element, like printing the span size of span of that particular time.